Hi everyone, welcome to another linear integrated circuit class. In the previous class, we explained we started with the practical limitations of op-amp. Specifically, what we did was focusing on the upper cutoff frequency of an op-amp and how that determines the frequency response of the system. What happens if we have multi-stage op-amps, and what is the effect of a multi-stage op-amp on the upper cutoff frequency. And we also solved some practice problems on multi-stage op-amp systems and the effect that has on a total gain and also the upper cutoff frequency. And the last part of that we did in the previous class was determining the upper cutoff frequency of multi-stage op-amps when all the stages are identical and have the same gain bandwidth and the same A noise. And the equation that we used was this equation that we had here. F2 of the system was F2 square root of 2 to the power 1 over n minus 1. And we also solved some practice problems using these equations. Today, we would focus on the lower cutoff frequency. So we are done with the upper cutoff frequency. Now we want to calculate the lower cutoff frequency of an op-amp. So for a standard op-amp, we already know that a standard op-amp could amplify the signal down to 0 hertz, which is basically a DC, if it doesn't have any coupling capacitor. So if we have a normal op-amp connected to a voltage source, imagine this is positive, negative, a normal not inverting op-amp. And if this is directly connected to a voltage source, since we don't have any coupling capacitors in the way of the input, this op-amp could technically amplify signals down to 0 hertz because it doesn't have any objects on its way. As I mentioned, and this was the terminology that I'm going to use again, a capacitor blocks DC signal, but it allows AC signal to pass. So if we don't have any coupling capacitor, we won't have any lower frequency limit. So in many cases, op-amps do not have a lower frequency limit or the lower cutoff frequency because they don't need it. But in some cases, one example is a single supply op-amp. We need to add a coupling capacitor. And when we add that coupling capacitor blocks any DC signals passing through and getting into the op-amp. Another application or another type of circuit that requires a cutoff frequency, a lower cutoff frequency, is a high pass filter. So anything that has a high pass filter, which we want to block the lower frequencies, also has a coupling capacitor. And one example of these high pass filters is when we have a noise at the lower frequency, which we call the humming noise or sometimes the white noise. And I gave you an example of electrocardiogram, ECG or EKG, they call it in Europe, which are used to measure heart rates. They are very sensitive to lower frequencies. And it causes, they cause noise on the signal and undesirable noise. So we want to filter that out. To filter that out, we can use a capacitor. Okay, now we have added a capacitor to get rid of noise. or any undesired DC signal. Now that has changed our cutoff frequency. How can we determine that cutoff frequency when we have a coupling capacitor? So in both cases that I mentioned, rather if it's a single supply op amp, which we saw in a single supply op amp, we need to separate the input from the DC power supply using a capacitor. Or if it's simply a high pass filter, the circuit design produces a low frequency roll-off or a lead network by introducing coupling capacitors. For single supply circuits, these capacitors are a necessary evil because, again, we need them to separate the DC power supply from the input. Without them, stage would quickly overload from the large DC input. So usually it looks something like this. We have an op amp, and this has a VCC, and we put a VCC, we separate it with a capacitor and feed it back, for example, as an input, as the input of our non-inverting or inverting amplifier, something like this, okay? So we definitely need it. One example of these single supply, by the way, is when we use them in these dusk to dawn, dusk to dawn light sensors. That's an example. Every op amp that has a battery, usually we use a single supply DC, and that requires a capacitor because we want to separate the input from our DC supply. And the only way that we can do that is with this capacitor. So another reason is that also signal sources and loads may be very intolerant of the DC bias potential. This could result in a distortion or component failure. Even if a circuit uses a normal bipolar supply, a lead network may be used to reduce interference signals. One example would be that a well-chosen coupling capacitor can reduce the 60 Hertz hum interference while hardly affecting the quality of the voice transmission. Where does this 60 Hertz hum interference come from? This is the frequency of the power outlets. We have 120, 60 Hertz. So if a audio amplifier is connected to an outlet as its power supply, that power supply AC would have a humming effect. As I mentioned, everything that in that circuit is going to act like an antenna. We have these microwave signals coming from outlets. The power line, especially if you're close to a power line, high voltage, it's like a large antenna that it's 1,000 miles long or something. You have these high power transmission lines acting like technically like a huge antenna, high power antenna. And we have it all around us. If you put a receiver here, you can easily hear that humming noise. And that when you have that's actually the 60 Hertz is in the range of the human hearing. We can hear between 20 Hertz and up to 20 kilohertz. So 60 Hertz, we can hear that. And it's a undesirable noise when you have an audio amplifier. It's going to have that humming noise. And we can get rid of that if we use proper coupling capacitors. Now, the same as the upper cutoff frequency, also if multiple networks are dominant, the resulting critical frequency will be the higher than the individual break frequencies. So for the upper frequency, when we had multiple stages, the upper critical frequency or the upper cutoff frequency was determined by the stage that had the lowest cutoff frequency. Do you remember? we had 3 stages. One of them was like 133 kilohertz, the other one was 250, the other one was 333. And the cutoff frequency of the system was like 133 or 125 kilohertz, which was the lowest cutoff frequency of the system. Here it's opposite. The cutoff frequency or the critical frequency, the critical lower cutoff frequency of the system would be determined by the stage that has the highest cutoff frequency. And I showed this with this graph already. So imagine you have a system, one of them has a cutoff frequency of 0, but the higher cutoff frequency is here. The other one is like this. What is the bandwidth or the frequency response of the system? The lower cutoff frequency is determined by the lower cutoff frequency or the highest one, and the upper cutoff frequency is determined by the black one. So our cutoff frequency is going to be the common mode in these two graphs. So this is going to be our FL and this is going to be our FH. So the lower cutoff frequency is determined by the op amp, which it has the red graph. The upper cutoff frequency is determined with the op amp, which has the black graph. And this is one way actually to create what we call a bandpass filter. The relationship is a mirror image of high frequency breakoff. And the other one we had F2, which was the upper frequency, was F2 square root of 2 in the power 1 over n minus 1. Here it's F1 over square root of 2 in the power 1 over n minus 1. If you decide to add coupling capacitors in order to reduce interference, remember that the op amp will need a DC return resistor. And this is an example. So this F1 system is when you have multiple op amps. For a single op amp, the cutoff frequency is determined by F1. And as you know from, I think it's in circuits 1, you also have it in circuit 2 as well. The cutoff frequency for an op amp is 1 over 2 pi RC. So the cutoff frequency is determined by this equation. F1 is 1 over 2 pi RC. Do you remember what F2 was, or the upper cutoff frequency? Yes, perfect. Gain bandwidth, or F unity over A noise. So as you can see, the upper cutoff frequency only depends on the op amp and the op amp structure itself. It depends on the characteristics of the op amp, which is the gain bandwidth, which we cannot change, and also the gain of the system, or A noise. But F1 has no relation whatsoever with the op amp. F1 is completely independent of the gain and the op amp characteristics. Okay. So no matter what op amp we change, we add the gain, anything, it's going to have no effect on the lower cutoff frequency. The lower cutoff frequency is only dependent on the RC circuit, which is technically, it's a coupling capacitor connected to the resistor. This is an example of our low frequency limitation system. We have an op amp, which in the input of the, first of all, let me ask this. What type of op amp amplifier is this? Is it a non-inverting or an inverting? It's a non-inverting. Why? Because the input signal is connected to the positive input, okay? And we added this RC circuit over here. And these two are the components that determine the cutoff frequency. So even if we didn't even have the op amp, this is a first order low pass filter. And you're going to learn about this. This is called what we call a passive low pass filter. It's a combination of a capacitor and a resistor. If you add an inductor or another capacitor, you create a second order. If you add more, you're going to create third order and so on. Usually we just use a first order or a second order. And in the next chapter that we speak about filters, I would explain the difference between a first order and second order. Second order has better response, better slew rates, a sharper response, but you need more parts. It's going to be more expensive and it creates its own challenges.
Oh, FC and F1,
I'm sorry?
FC and F1 are the same.
FC and F1 are the same, yes. So it's going to be 1/2 pi. This is FC, C means the cutoff frequency. Okay, but if we didn't have the op amp, we would have one cutoff frequency, and that would be the lower cutoff frequency. But since we have the op amp, we would have two cutoff frequency, F1C and F2C, or FL and FH, or F low and F high upper. If some books I actually show it with F1, F2, some show it with FL, FH, or FL, FU, which is upper cutoff frequency. So for this example, we have 100K resistor to properly bias the op amp, and we have a 0.1 microfarad or 100 nanofarad capacitor connected to it. As you already know from the homeworks that you have, the input impedance is also determined or equal to the 100K resistor that we have here, because the input impedance of the op amp is close to infinite. So if you have an infinite resistor in parallel with 100K resistor, that input resistor would be closer to the smaller resistor, which here is the 100K. Assuming a relatively low source impedance, which is impedance of Vn, the lead network simplification boils down to the 0.1 microfarad along with the 100K. The critical frequency is calculated as shown, FC, or it's going to be 1/2 pi RC, which is going to be 1/2 pi times 100K times 0.1 microfarad, which gives us 15.9 hertz. To sum up then, when using general purpose op amps, if no signal coupling capacitors are being used, the gain response extends back to 0 hertz. But here, since we have this coupling, the lower cutoff frequency is limited to 15.9 hertz. And again, you can read faster than me. Let's solve a practice problem, because I think practice problems and examples would help you better understand the system. So imagine we have a resistor and a capacitor, again connected to the positive, negative side of the op amp. C is equal to 0.2 microfarad. R is equal to 500. Oh, let's make it 250. No, 500K is okay. 500K. Vs is 4 cosine of 377T. The feedback resistor is 100K. The Ri is equal to, let's say, 25K. I want you to find the frequency response, which is F1 and F2, to be able to draw the graph for the frequency response. And I want you to also find V out. And this op amp is a U741. U741 has a gain bandwidth of 1 megahertz. Give you 5 minutes to solve this one. Yeah, small 1 megahertz is a gain bandwidth product. Why did I- So gain bandwidth is 1 megahertz. Do you need more time or do you want me to solve it? Okay, what was F2 that? Okay. So yes,
Yes.
okay. So first thing to find, you need to find a noise. What type of amplifier is this? It's a non-inverting. A noise is 1 plus RF over RI, which is going to be 1 plus 100 over 25, gives us 5. F2 is equal to the gain bandwidth over A noise, which is 1 megahertz over 5, gives us 200 kilohertz. Now, what is V out? V out would be A V times Vn. AV is the same as A noise because it's a non-inverting amplifier, which is going to be equal to 5. So it's going to be 5 times 4 cosine of 377t, which is 20 cosine of 377t. So this is going to be 20 sine of 377t. Okay. Now what about F1? It's 1 over 2 pi RC, which is going to be 1 over 2 pi. R is 500K, and C is 0.2 times 10 to the power of negative 6. So therefore, what is F1 equal to? 1.59 hertz. Did you get the same result? Okay, perfect. So upper frequency is 1.59. I'm sorry, lower frequency is 1.59. Upper frequency is 200 kilohertz. And V out is 20 cosine, or the gain is 20. So I'm going to try to draw it here. So our lower frequency and the upper frequency. This is 1.59. This is 200K. And the gain here, the maximum gain that we have is 5. Or in other words, in voltage, it's going to be 20 cosine of 377t. Okay, do we have, so another question, the reason that I put 377t is, another question that I have, do you think, imagine that this is an audio amplifier. Do you think we're gonna have a humming noise in the system? Yes, why? Yes, 6 hertz is around here. You're gonna definitely have a humming noise in the system. Okay. So it's not a very good design, I would say. 66. Is this part clear? Can I go to the next? Yes, okay. Oh, let's solve another one, then I'm gonna start with this part. Let's solve it for a multi-stage. So imagine we have, again, something similar to what we had. This capacitor has let's say this is 20K. This is 5 microfarad. And this is connected again to another 30 microfarad, and this is 60K connected again to another positive and negative. This is 20K. This is 2K, 10K, 5K. We want to find F1 of the system and F2 of the system. Again, both of them are the U741 or LM7, the 741. So both of them are the same op amps, and both of them have a gain bandwidth product of 1 megahertz. Okay, what is the F1 of the system? So first we have to find F1 and F2 for the first part, and then F1, F2 for the second part. So for the first part, F1 is 1/2 times 2 pi times 5 10 to the power -6 times 20 times 10 to the power 3. So what was F1 for the first one? 1.5 millihertz. Hertz. Okay, let's round it up. 1.6 hertz. 1.6 hertz. All have the same number. Right. What about the F2 for this? It's going to be the gain bandwidth product and 1 megahertz over the A noise, which is going to be 3. So it's going to be 333 kilohertz. What about the F1 for the second one? It's going to be 1/2 pi times 30 times 10 to the power -6 times 60 times 10 to the power 3. What is F1 for this one? 88 millihertz. Yes. Millihertz. What about F2? It's going to gain bandwidth product, which is 1 megahertz over 1 plus 20 plus over 2, it's going to be 11. So it's going to be what? 88. 90.9 kilohertz. Since they have different frequencies, we will pick the lower frequency, which is higher, which here is 1.6, and the upper frequency, which is lower, which is 90.9 kilohertz. So F1 would be 1.1 hertz, and F2 would be 90.9 kilohertz. I don't have time to solve another one which have the same, but I'm going to do it probably next week because I want to finish this. Slew rate and power bandwidth. So as we noted in the previous slides, these op amps have a compensation capacitor, which is used to control the open loop frequency. We can shift the lower cutoff frequency. And the signal developed across the capacitor will be amplified in order to create the final output signal. In essence, this capacitor serves as the load for the preceding stage inside of the op amp. Like all stages, this one has a finite current output capability. Due to this, the compensation capacitor can be charged no faster than a rate determined by the standard capacitor charge equation, which is I is equal to, we already know C dV over dt. In other words, dV over dt is I over C. dV over dt is our slew rate, which is also called slew rate. We measure it volt per second, but usually in this particular case, because the switching speed and slew rate is so high, we measure it by voltage over microseconds or milliseconds, but most of the time it's volts over microseconds. So the rate of changes of voltage versus time is dV over dt, which by definition is called the slew rate. Slew rate is very important in that it helps determine whether we have a, let me put it this way, whatever we need a high-speed op-amp or lower-speed op-amp is completely determined by the slew rate. Sometimes this slew rate limits our frequency response. So usually it's more desirable to have a op-amp with a higher slew rate. in most cases, if we have a high frequency system, like a communication system, the slew rate would limit our frequency of response. In this particular example, if a 30 picofarad capacitor is used, and the current is 100, changing by 100 microamps, the slew rate is 3.3 volts per microsecond, which is in the range of a 741 op amp. But if the current was higher or the capacitor was smaller, then it would be out of range for a 741 op amp. Slew rate of a capacitor is determined by two things: the capacitance itself and the rate of current change. It's always better to limit the current charge or use a larger capacitor to decrease the slew rate. But if we want to have a rapid responding op amp system, we need to have a high current, small capacitor system. And what does this mean? Slew rate is basically the rate of charge for a capacitor. The smaller the capacitor is, it's going to charge faster, reach its maximum faster, or you can put higher current into it. One example that I could give is a battery charging system. If you want to fully charge a battery, a 12-volt battery, you can rather decrease the battery capacitance, use a smaller battery, and charge it in 1 second. Or you can use high current, which is a DC fast charging, which could be used in a car, for example. It's the same thing that you have with your phone. You can use high current, which is a high power charging station, like a 40 watt. But if you want to use a low current and slow charging, which is 5-10 watts, it's going to take a long time to charge. The slew rate for different op amps are different. For 741, it's 0.5 volt per microsecond. But we have op amps, which are expensive op amps, could go up to 1,000 volts per microsecond. Usually, in most cases, a 411, which I showed you another example in the last chapter, works perfectly. You can see that a 411, the slew rate is 30 times of a 741. Much faster op amp, but it's at the same time more expensive. What does this slew rate mean? Is that, for example, if you want to charge the system to 10 volts, for a 741, the slew rate, if it's at 0.5 volts per microsecond, that takes 20 microseconds to go up to 10 volts. For a system that is 3.3 volts, it takes 3 seconds. For a system that is 20 volts, it takes 1 second. So if we want to charge up to 20 volts, for this one, it would take 40 microseconds. For this one, it would only take 1 microsecond. So 40 times faster than in 1 microsecond. I think we're over. We don't have enough time to continue. We're going to stop at this point. One thing that I want to mention, the in-class students, we're going to have a review session on this Thursday. I'm going to solve a few questions for upcoming exam. I would highly recommend you come to the review session, because the questions that you're going to have on the review sessions are going to be very similar to the questions that you're going to have on the exam. If you have any questions, just please let me know. Thank you so much.